So, and we can do this with a graphing calculator so you can see. We know the graph of sine in the first quadrant is this. Pi over 6 is right here. So the value, which is 1/2. So this is somewhere here is 1, this is 1/2. So it's guaranteed that this line is the tangent line at that point. And if I want to approximate sine x in the vicinity of pi over 6, either to the left or to the right, it's okay if I use the line. The numbers will be very close. There will be a tiny error, but they will be very, very close. That's what this means. So this is the L of x. Do you need me to illustrate with a graphing calculator? Or is it clear what we are trying to say here?
That's clear. Thank you.
Thank you. If you find any problems in WebAssign, please bring them to class next time. That's all I had to say, unless you find something that you need help with and you want me to go back to. Anything that you would like to, or you find. The last section from chapter 3 is 3.9, related rates. What does this mean? Imagine that I cannot draw. I'm not good at drawing, but let's say this is a deflated balloon. Let's say it's in the form of a sphere. So I pump air in the balloon, and at some stage has this shape. I pump in more, and then it's at this shape. What happens here? Obviously, the radius changes. So the radius at this stage is this, R1, at this stage is R2, and depends on where I stop. What else changes? So obviously, this is a function because it changes with respect to time. So dr over dt will be the rate of change of radius with respect to time. So I created a function already, and I created its derivative. What else changes? The volume. So this is volume V1, and then I pump more air. This is volume V2. I created a new function, volume, and it has a rate of change. So dV over dt will be the same thing, but the rate of change of volume with respect to time. You can say there is another one that you can create. Yes, it's the surface area, S1, S2. So yes, ds over dt is another function of everything the same, all those words, but this time is a surface area with respect to time. So all these rates of change of different functions involved in the process of pumping air into a balloon, they have a rate of, all these rates of change are related, meaning when one changes in some direction, it triggers a change in the others in the same direction or inverse direction. It may happen, one or the other, positive or negative, but those related rates, those rates are related through an equation, are related through measurement units, they are related through the magnitude of the rate of change itself. That's why we call them related. They have something in common. They happen at the same time, and one triggers the other, and also the magnitude of one changes the magnitude of the other. So that's what we mean by related rates. I can talk about related rates for a month, honestly. There are different types of problems, all different, I would say, all have something in common, and they're all different in different ways. So I will, for the rest of the time, we have an hour, I will present as many problems as possible so we can discuss them with related rates. Okay. So this is at the end of 3.9. And I don't know what to start with. I'm gonna just name a few, and you'll tell me what you would like me to start with. This is an interesting situation in which you see there is a pile of sand, and it's in the form of a cone. And it says that it's not sand but gravel is being dumped from a conveyor belt into this form at a rate of 30 cubic feet per minute. And it piles up in such a way, it's in the shape of a cone, whose diameter at the base and height, as you see that in the picture, are always equal. How fast is the height of the pile increasing at a particular instant when the pile is 10 feet high? Would you like to start with this one?
Yes.
Okay. So let's draw the cone. I would like to refresh your memory on the volume of a cylinder, which is area of the base times the height, area of the base multiplied by the height. But the area of the base is, as we just had it, like a circular disk, pi r squared times the height. And since I put lowercase r, I'm going to write lowercase h. Doesn't matter, really. I can change it also into pi r squared h. Doesn't matter. But why I mentioned this is because the volume of the cone is the same thing, but with 1/3 in front. So it's easier to remember them together. 1/3 pi r squared h. So this is a side comment. Okay, so I will read the problem one more time. And we'll make some notes once we read the problem. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. So I have to stop and ask myself what this represents. And that's my starting point, and that's crucial to understand what that means. What is it?
Constant value.
Say it again.
The value that is constant, that doesn't change.
Volume is not measured in cubic feet per minute. It must be something totally different.
It's the rate that the volume is changing.
With respect to time. Very good. The measurement unit tells us that this is a rate of change. It must be a derivative. It must be the rate of change of volume with respect to time. Thank you, Carson. Very good. Moving on. So the cone, the height of the cone and the diameter of the cone are always equal. So the height and the diameter are always equal. And the diameter we know is the same with what? Anyone?
Diameter is the same as twice the radius.
Very good. Perfect. Thank you, Mark. Okay, so now we are asked how fast is the height of the pile increasing when the pile is 10 feet high? So what are we asked to determine? When the pile is 10 feet high. How fast is the height of the pile increasing when the pile is 10 feet high? What are we asked to find? Anyone?
The rate of change of the height.
Great job, Jordan. Thank you. Exactly. So this is what we are given. This is also given. The rate of change of volume with respect to time, which is constant. And we're asked to find the rate of change of the height with respect to time, of course, at a particular instant when the height is 10 feet. Where is our starting point? What do we need to start with? What is the first step? First thing that I need to look. Say it again.
Find the derivative, find dH dt of the cone formula.
So, no. So where is the starting point? The starting point is with what I have. What do I have?
You have the change in volume with respect to time.
So my starting point must be the volume. So then the volume must be pi r squared h. Now I have to relate it to this. What should I do? And at this point, we have to look at the fact that I know the rate of change of volume, but I have here two variables, and I would like to get rid of one if I can. What is the one that I will not get rid of? Because I need it. I have to have it. I have to have it in the answer. I cannot get rid of it. Which one I will
You have
not?
that height.
Yes, this has to stay. Stays. But is there a way of getting rid of the radius? That would be fantastic.
Can you write it as h over 2?
Of course, thank you very much, Carson. Indeed, from here, the radius will be h over 2, of course, everything squared. So now the volume is indeed a function of, it's a function of time. So I'm not going to put, it is a function of age as well, but I don't want to confuse you. So I'm not going to write V of, I'm just going to write V equals pi r squared over 4 times, I meant h. H squared over 4 times h. The volume equals pi over 4 h to the third. Now keep in mind what we have in here. We have two functions of time. Good. So we know something already from this chapter, that we can do something to both sides to determine what we are asked to find. Any suggestions? Anyone? Please.
Before that, isn't the volume of the cone doesn't have the 1/3 in front?
Thank you. I will, no excuse. Thank you. Thank you. Thank you. So pi divided by 12 h cubed. Thank you very much. I wrote it here, but I didn't write it here. I was preparing you, but I wasn't preparing myself to copy the right formula. Thank you. No, I wasn't trying to see whether you were asleep or not. No, I talk too much. Thank you. Okay, good. So what do we do next? What are we asked to find?
H.
Say it again.
Is it h?
No, we're not asked to find h. We're asked to find a related rate to the rate of change of the volume. If this isn't clear, please let me know. Maybe I didn't explain exactly what we're trying to do. If no one says anything, maybe I didn't explain it correctly. Anyone?
Is it the V of H?
We're asked to find the rate of change of the height at a particular instant. That's our question. So what should we do here to both sides to find that? Anyone? Javon, what do you think we should do?
Move the 3 to the front.
You're saying to differentiate both sides.
Yeah.
Good. So what do we have on the left-hand side? Good.
5/4.
What do we have on the left-hand side?
dv dt.
Of course. What do we have on the right-hand side?
Three pi 12 over 12 H2.
Times d.
That's why I wrote here that we have two functions of time. One is the volume, and the other one is the height. As I mentioned initially, we pump air in a balloon. R is a function of time. S is a function of time. V is a function of time now, because they're changing. Good, very good. And now we are after this. All I have to do is simplify, multiply both sides by 4 over pi h squared. Let me write it one more time for everyone to see what I'm doing. So dv over dt equals pi h squared over 4 dh over dt. We are solving for this. I will multiply both sides by 4 over pi h squared. So 4 over pi h squared dv over dt equals dh over dt. I will rewrite it from the other side. So dh over dt equals 4 over pi h squared times dv over dt. And now, only now, I would say when h equals 10 feet. This was given to us as 30 cubic feet per minute. And this now is 100. So now I can continue with 4 times 30 divided by 100 pi. And I will approximate. And let's see what we get. So I'll simplify and I get 25. And I'll simplify and I'll get 6. So I'll divide 6 by, in parentheses, 5 times pi. Approximately 0.382. Measurement unit.
The feet per minute.
Thank you very much. It's the rate of change of height with respect to time. Who said that?
Javon.
Thank you. Very good. If you want it exact, you can keep it as 6 over 5 pi feet per minute. I'm writing that because in WebAssign you may get, you may be asked to present. Okay, very good. Let's look at, yes. So here it is, a spotlight on the ground. We could probably look at and choose problems from Weber